Concentration, please. Last week we started on differential calculus, and we were using the table of standard derivatives to differentiate a range of different functions. I was just going to slip through some examples. So 12x cubed, it's in the form of ax to the n. The process here is we multiply by the old index, 3, times 12, take 1 off the index. So the integral, the first differential of 12x cubed is 3 times 12, which is 36x squared. If we're in a position where we've got a term of x or a function of x that's got x below a fraction, we need to rearrange using laws of indices to bring the x up to the top. So that's 12x to the power of minus 3, and then we take 1 off, we multiply by minus 3 and then take 1 off, so we have 36 times x to the power 4. Okay, we can then return that to the original form if we want to by putting the x term underneath and making it a positive index. Okay. Then we had a look at a couple of special cases. What happens if we differentiate a constant, for example 6, any number to the power 0 is equal to 1, we can add that to the constant and not change it. We then differentiate and we end up with 0 times 6 times x to the minus 1. Well, 0 times anything is 0. So if you differentiate a constant, it just disappears. Okay? And we made that statement there. What about when we've got a constant times our variable, 6x? We can write just x on its own as x to the power of 1. Then it looks like ax to the n. And we can bring that index down and multiply. So 1 times 6 times x to the 0. X to the 0 is 1, so that's 1 times 6 times 1 is 6. So if we differentiate 6x, the x just disappears and we're left with a constant. Differentiate 10x, x disappears, left with 10, and so on. And then we looked at examples where we got roots. So if we want to differentiate 3 times the root of x, we need to write it in indices form. So we write the square root of x as x to the half, and then we can apply ax to the n. If we've got something like the cubed root of x to the power of 4, that's under the line. First turn it into index form. So the 3 comes as the denominator of the fraction, the 4 as the numerator. Then bring the x to the power 4 of the 3 up to the top line. You've then got in ax to the n form. And then we're going to apply the same rules to multiply by that index and take 1 off the index. Multiplying out at the end up with an answer. Okay. We had a look at where we've got more than one term. So we got several x terms added together. Right, so if we want to differentiate where we've got a number of x terms, so we've got 5x to the 4 plus 4x, we've got minus 1 over 2x squared, we've got a square root in there, and we've got a constant. What we simply do there is we differentiate each term separately and add them all together, or subtract as necessary. So 5x to the 4 becomes 20x to the 3. 4x to the 1 becomes a constant, which is 4. Half of x to the minus 2, that's minus 2 times a half. That makes it a plus single x to the minus 3, and so on. So where you got more than one term, added together or subtracted, just deal with each one separately, differentiate each one, and sum the the results. We had a look at some other functions. So 3e to the 5x, that's in the form of e to the power of ax. So we bring that 5 out, 5 is the a in this case, and multiply, and e to the 3e to the 5x remains. So we end up with 15e to the 5x. ln. So differentiate 6 ln times 2x. It's in the form of ln times ax. So the differential of ln x is 1 over x, I believe, looking at your tables. Yeah. You end up with 6 over x. 6 times 1 over x. Yeah. And then I think we didn't do anything else after that. There are some cosine ones down the bottom, maybe no there isn't. Okay. So, what we're going to look at this week, moving on from that, will involve plenty in doing them basic differentials anyway, because they'll be included in the formula we're going to use. We're going to look at some the second half of your table differentiation. It includes the formulae for differentiation, which is that. We've got a product rule, which we use where we've got y is equal to one function of x, for instance, multiplied by a second function of x. So u and v, if u and v are both functions of x and they're multiplied together, we have to apply the product rule. If we have y is equal to u over v, where u and v are both functions of x, we've got a quotient, named fraction, we use the rule. And then if we have a function of a function, so we've got something like a quotient, but inside it has also got a function of x, so it's a function of a function, then we apply what's called the chain rule. Alright, so we're going to go through today some examples of rules. Yep. And the thing here is recognizing what you need to use. Look at the function so that you can apply the right function in an exam situation, as well as the maths involved. Okay? So one involves the product rule. We're looking to find the differential of y is equal to 3x squared times sine 2x. So this is one function of x, and this is another function of x, and they're multiplied together. Yeah. It's one times the other. Use product rule. Product rule says dy by dx is equal to u times d by dx plus v times du by dx. So that's the formula we need to use to solve, just differentiate 3x squared and sine 2x and multiply them together. That doesn't work. Okay? You've got to use that formula. So this is what we do. We say, and what I like to do here is split my page into two. And I'll go over here, u equal 3x squared. And on this side, let v equal sine 2x. Yeah. Then what we need to do is differentiate both, i.e. find du by dx and dv by dx. So how do we differentiate this one, 3x squared? That's in the I and x. So what's the process from last week? Yeah, so we multiply by the old index and take the index. So that's 2 to so du by x. This is in the form of sine x. Differential for sine. A cos AX. That we need from the formula. We've got dv, we've got by dx. So what we then do, so we can write dy equals u, that we call u, 3x squared. And before, help with getting all the signs right is put each term in brackets to start with. So 3x squared times dv by dx, which is 2 cos 2x. And then we've got to add v, which is sine 2x. And multiply that by du by dx 6x. Move. Six x in there. Yeah. And then we can do some simplification in terms of we've got two constants there multiplied by each other. So we can write is equal to 6 x squared cos 2x plus 6x sine 2x. Three x squared cos 2x, 3 times 2, 6x times cos 2x. Here, sin 2x times 6x. So I'll just put that in front. Yeah. Any further simplification you can see? What can we take outside the brackets? 6x. 6x x cos x. Alright. In an example, I would expect that or that as a valid solution. Okay. So, valid solution to that. Differentiate. We have to use rule. We'll look at another example. Determine the rate range of voltage given that V is equal to 5t sine 2t volts. So V is equal to 5t sine 2t volts. So it's got a question that's got an engineering relationship, and it wants to know the rate of change of voltage when t is equal to 0.2 seconds. So the rate of change is the differential. It's d dt. Remember that slope of the graph at that point where 0.2 seconds is. Alright? So what we'll do with this one, let's see if we can graph that that function and see what the slope is where t is equal to 0.2. Right? So we need to differentiate this and then put t to 0.2 in the differentiated function, find out what the rate of change is after 0.2 seconds. Right? So let's make a start. What we're gonna let u equal? Let u equal 5t, yeah. Let v equal and then we need to differentiate du by dt. dt. This one is plus 5 and dv by dt is so it's 2, bring the 2 out, change it to cosine. I'll remind myself of the formula before I want to get it wrong. U dv by dt plus v du by dt. So we put our numbers in. U was 5t. dv by dt is 2 cos 2t. V was sine 2t. I've got to multiply that by half. Yep. Everyone see where those come from? Yeah. Yeah, but we're not working with x now. We're working with is our function is v is the dependent variable, like y in a standard function, and t is the independent variable. Yeah. So you have to just change the letters that you use. And rates of change are usually by dt, because we're talking about how fast is it changing with time. Yeah. So rates of change end up t. Then we can simplify. So we've got 5 times 2 is 10t cos 2t plus 5 sine 2t. Yeah. So, and that is dv by dt, which is the rate of change of voltage time. What we do then is say when t equals 0.2 seconds, dv for 10 times 0.2 cos 2 times 0.2 5 sine 2 times 0.2. We put that in the see what some get the mention last week. Anything always radians. So before you calculate is in radians now. I'll make a note of that on here. Yeah. So we've found the formula for the rate change, and then we've inserted the time at which we want to know what the rate of change is. 0. And got the and we want to find dy by dx. So we've got y is equal to, for instance. Yep. Right, Nathan. Lead us through it. So we've gone, let u equal 2x cubed. Anyone not done that? Of those that struggle with it. Yeah? Nathan? Yep. Du by dx equals 6x squared. dv by dx is minus 3 sine 3x. Everyone got that far? Yeah? So then that's a matter of putting those four things into the formula for product rule. So dy by dx is equal to u, which is 2x cubed, times minus 3 sine 3x plus v cos 3x times 6x squared. Everybody got that? Yeah? So Nathan, what have you done then? minus 6x cubed. That comes from multiplying that 3 by that 2x cubed. That's you, not... Yeah. So, sine 3x plus 6x squared cos 3x. Yeah. Well, what's the answer he's given? Yeah. Right. What he's done is he could write that with this on that side and the minus on that side. Do you see? That's all he's done. Is he's written it as 6x squared cos 3x minus 6x cubed cos 3x. Yeah, and then simplified by taking 6x squared outside some brackets. Oh, sine 3x. Yeah, that's a right answer, but it's not so easy to simplify because you've got the negative sign up front, and if you can get rid of a negative sign up front, you usually do. It depends whether I ask for it in its absolute simplest form or not. I mean, that's a right answer. Yeah. So then we can go 6x squared brackets cos 3x minus x sine 3x. There's a problem with Mr. Bird's answers sometimes because he simplifies to what he thinks the simplest form, and you can't always see. That would be fine. That's a correct answer. So if you were looking for a value for the rate of change and you put x is equal to 3 in it, you'll get the same answer as if you put x is equal to 3 in that one. If you're unsure whether your answer is exactly the same as his answer, put a value for x in. Choose a value for x, 3, put it in your formula, get an answer. Put the same value of x in his formula, you get the same answer. They're equivalent. Okay? Understand that? That ain't going to help you in... I've marked that right, yeah. 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 Alright? So are you okay with that? I'm going to give you about another 5 minutes to have a go at the second one, and then we're going to have to move on. Quotient rule. And then but we're going to have to move on because otherwise we'll get behind. Alright? So, this second example is y is equal to the square root of x cubed as a function of x, yeah, multiplied by ln 3x, another function of x. Yeah? So, we're going to make u equal to square root of 3x. And v is equal to ln 3x. That's what it is. But we need to write this in index form. U is equal to, and I've seen an example where not wanting to pick anybody out, but they've written du by dx is equal to, we've got to write this in index form, x to the power 3/2. Because now it's in ax to the n form. Is it not? Yeah? This one, we don't need to do anything with. dv by dx is equal to 1 over x. 3 disappears. That's what the table says. Yeah. Differentiate this. du by dx, this is where people are coming up. That we've got, remember what the process is. Multiply by the old index. 3 over 2. Times x, and we've got to take 1 off the index. So that's 3 over 2. We've got to do 3 over 2 minus 2 over 2. Leaves 1 over 2. Alright? Which can be written as 3 over 2 times the square root of x. Put it back in that form if we want to. Alright? Leave it in that form to start with if you want to, that's fine. So now, dy by dx is equal to u, is it not? U first, yeah. 3 over 2 square root of x times dv by dx, 1 over x, plus ln 3x times u was x to the 3 over 2. I'm trying to see how he's got what he's got here. Which ones? Is it u x to the 3 over 2? Let's put that in there. X to the 3 over 2. Just shows how easy it is to get it wrong. 1 over x plus v ln 3x, and this should be 3 over 2. So that shouldn't be 3 over 2 there. This should be 3 over 2 x to the half. You can do. I'm just trying to see if I can see where he's got his simplification from. We've got root x outside the brackets. Yeah, I think he is too. You managed to get it, Nathan? You can see it, can you? Right, that's x to the 3 over 2. We could write that over 1 multiplied by 1 over x. That is x to the 3 over 2 divided by x to the 1 equals x to the half. Not minus the half, or the square root of x. So that term there becomes the square root of x. And that's why he's got the outside brackets, because then he's got square root of x in both sides. But put x equals 1 into our formula and get an answer. Where his simplification comes from is, as this over here has shown you, that bit there is square root of x plus 3 over 2 square root of x ln 3x. As there, he's taken square root of x outside some brackets. 1 for that bit plus 3 over 2 ln 3x. That's where the simplification comes from. Alright? Anyway, we must move on, but it flags up needs practice. Okay? Doesn't it? Yeah? Right. Move on to the quotient rule, where we've got two functions of x when one is divided by the other. So we've got a fraction. Our example here, and the process is similar, okay, it's just that the formula is different, and we must make sure we get them the right way round. When we're adding together, when we're multiplying together, order doesn't matter. When we're subtracting, order does matter. So we've got a function y is equal to 4 sine 5x divided by 5x to the power of 4, i.e. as a function of x divided by another function of x. Obviously they're different, because otherwise it would just equal 1. Alright? So we've got a quotient, we need to use the quotient rule. So what we do is we let u equal 4 sine 5x, and it must be the numerator. We can't let u equal 5x to the power of 4. In the product rule, you can get them the wrong way round and still get the right answer, but not in the quotient rule. Okay? And we let v equal the power of 4. And then we differentiate both. So differentiate 4 times 5x, 4 times sine of 5x, 20 cos 5x. And du by dx for 5x to the 4, yeah, 4 times 5 is 20. So, the formula dy by dx is equal to I'm going to write the formula first because I want to make sure we get it. We need to get it right. It's v times du by dx minus u times dv by dx, and they must be in order. All over v squared. So then we put our result of that, dy by dx is equal to v 5x power 4 times du by dx 20x cubed So 20 cos, that should be V. Probably just my writing. Cos 5x minus U by 4 sine 5x times dv by dx 20x cubed. And all of that goes over v squared. That's 5x to the power of 4 squared. Plus, hang on, just find the example. Last thing I want to do is get it too wrong. Right. So let's look at how we might be able to simplify this. 20 times, we look at this, 20 times 100, x to the 4 cos 5x minus 80 80x cubed sine 5x all over. How can we simplify that? Now, when we got that a power to another power, what do we do to the powers? We multiply them. Laws of indices. So we got a square of 5, 25, x to 2 times 4 is 8. Yeah, you can. Can you see what you can take outside some brackets on the top? More than that. You can take out 20x cubed. That'd be 5x. Where minus 4 sine 5x. And all of that is over 25 x to the 8. Well, we're going to leave just x in that one. But then we can also take 20 will go in. Yeah. Why these do we get back to 100x? We end nothing with the term, and 20x cubed times minus 4 equals minus 80x to the 3. And actually what you can do, because 20 and 25 will divide by 5, you can put 4x cubed sorry? Yes, you can actually. You can divide top and bottom by 4x cubed. 5x cubed, sorry. Final answer, simplest form, is 4 over 25 x to the 5 gets 5x times 5x. I'd take that form any day of the week in the exam question. In fact, I'd be quite happy to take that one. Yeah, I'd like to see this turn move from that to that, but I'll take that one. All right. So, another example of using the quotient rule. Determine the gradient of the curve. Y is equal to 5x over 2x squared plus 4 at the point where x is equal to root 3 and y is equal to root 3 over 2. Yeah? So, first of all, we've got to differentiate. So we've got y is equal to 5x divided by 2x squared plus 4. What are we going to let y equal? Let u equal? And let y equal 2x squared plus 4. Differentiate. V. Slow down. du by dx is equal to dv by dx is equal to, that's just 5, yeah, because that's x to the 1, so the x term disappears. And dv by dx is what happens when you've got to differentiate each of these separately. So we differentiate 2x squared, 4x to the 1, we don't bother to write the 1, differentiate a constant, disappears. Yeah? So now we apply quotient rule. dy by dx is equal to v 2x squared plus 4 times du by dx 5 minus u, which is 5x, times dv by dx, which is 4x, and all of that is over v squared 2x squared plus 4 plus 4 all squared. So start trying to simplify. What are we doing here? What happens if we multiply these brackets out? (10x squared) plus 20. Got to multiply 4 times 5. Minus all over 2x squared plus 4 all squared. What, down the bottom there? Yeah, you can do. I don't know. No, I think if you multiply what we're looking at there is that is effectively 2x squared plus 4 multiplied by 2x squared plus 4. If you multiply them out, you're just going to make a bigger mess than you've already got. Just so you can, at the moment, leave it like that. Yeah? So what does that top line actually come out to in its simplest form then? Yeah, so what the best thing to do is, look, we've got 20, take away 10x squared, take away 20x squared is minus 10x squared, all over 2x squared plus 4 all squared. And then the question is saying, let x equal root 3. So we need to insert root 3 in place of x in that formula. Y equals 20 minus 10 times root 3 squared over 2 times root 3 squared plus 4 all squared. No, you're not differentiating now. You're finding, you've differentiated, that's your differential, this one, and you're inserting, now you're trying to find what the differential is equal to at a certain value of x. Yeah? What is the square root of 3 squared? Yeah, 3. Go on. Yeah, because the question says find the gradient or the slope at the point root 3, that's the y, at the x coordinate and y coordinate. We want the x coordinate, don't we? We want a value of x. Yeah. Minus 0.1. Yeah, minus a tenth is minus 0.1. That's what I've got on there. Equals. You don't need the y, you only need the x. So what you've got a graph, I don't know what shape it is, right? You've got a graph something like that maybe, okay? And we've got this point here where x is equal to root 3 and y is equal to whatever that is. I can't remember, but y's got a value. Yeah, and what the answer you're finding is, what is the slope at that point? What is the gradient at that point? Tangent to, yeah? Minus 0.1. Alright? Okay? Right. 10:30. We'll